Section 7.3, using functions involving e. So far what we've looked at are exponential functions of growth and exponential functions of decay. And those were based off of some variable b that we called our base. And that base was an integer or a decimal number of some sort. And from that we derived some critical movements to help us determine what the graphs of these functions look like. And then we applied some of our exponential growth or decay models to finances when we talked about compounding interest. And today we're going to look at another exponential function. So it's going to model and have the same behavior as the growth and decay functions we've seen in the previous few sections, but this one has a special base, and it's called the natural base, e. In fact, if you looked on your calculator, you'll probably find a button that had ln on it, and then maybe right above that button would be an e to the x key, or you might even have a separate e to the x key. Well, that's what this is all about. It's called the natural base. And all it is it's a fancy base value. So when we, in talking about our exponential functions, generically speaking, we have a generic exponential y equal ab to the x power. Well, now what we do is we just exchange that b. In very simple terms, we just become a e to the x. Now, we are going to introduce another variable that is a multiplier with that x value up there. But in simple terms, that's all we're doing. We're just changing our base value there. It's called the natural base. It's an irrational number, which means its decimal never terminates, never repeats. And there's an example of what it is, approximately 2.7182, and then keep going. Where it comes from is it comes from an expression of 1 plus 1 over n all to the n power. And this is kind of our first look at see what a limit is. If I put huge numbers in for n, I keep putting bigger and bigger numbers in for n in that expression. Let's say we put 100 in there. 1 plus 1 over 100, all to the 100th power, or 1 plus 1 over 1,000, or 1 over 1 over a million. That value that that expression equates to would be getting closer and closer to that 2.718. So that's where the number e comes from this expression. Let's talk about, before we get to the graphing component, the fact that we're dealing with exponential numbers, doesn't matter whether it's a natural base or otherwise, we still obey the same properties of exponents that we did back in Chapter 6. So these should be just real quick reviews of some of those properties. In this first one here, A, we're multiplying like bases, and that meant that we simply added the exponents together. And then in B, we have bases that are dividing with each other. Now the 60 and the 12 are not being affected by those powers of 8 and 3 respectively, so they're just a coefficient. That means they just simplify. 60 divided by 12 is 5. And then we have e to the 8 minus 3 because we're subtracting. And we get 5e to the 5th. So those are our product of powers or our quotient of powers. Here we have a power of powers with c. Remember that a power on the outside raises everything on the inside, that power value. So we have negative 10 being raised to the power of 3. And then we have this e to the negative 5x being raised to the power of 3 as well. So this becomes negative 1,000. And this becomes e to the negative 15x. And then we want to write positive exponents. So we just move that e to the negative 15x into the denominator. Negative 1,000 over e to the 15x power. So those are some reviews of some of our simple exponential properties. Calculator-wise, just to make sure we're understanding where these buttons might be on our calculator and how we use them. E to the 6. So it depends on your calculator. Sometimes you put the 6 in first and then hit the e to the x button. Or sometimes you hit the e to the x button and then put the 6 in, it just depends. But if you did e to the 6th power, you would get 403.428. Approximately. And e to the negative 0.28 power, I could rewrite it as 1 over e to the 0.28 power. And in that case, I would get 0.756. Again, these are approximate values because we are rounding here. All right, so that's just some calculator use. Let's talk about the graphs. So because the natural base function is just a growth or a decay function with a different base value, their graphs look the same. We talked about the growth functions looking like a skateboard ramp, driving up the skateboard ramp left to right, or a plane taking off. The decay function, you can look at it as dropping in on your skateboard ramp or a plane landing type of thing. And here's where we're going to peek at this r value. So you'll notice our equation y equal a e to the rx power. This r value is different than what we normally see for our bases. Sometimes that r is just 1, and we just get y equal a e to the x. So when our a, which again our vertical stretch factor, is positive, and our r is positive, then we have an exponential growth. When the a is positive, but the r now is negative, I will get the decay of this function. And then here are some of the graphs for those, both growth and decay. And in terms of their critical movements, parent function-wise, we're talking about a parent function of y equal a e to the rx. A has the same parent functions as a y equal a b to the x, a b to the negative x. So here are our critical movements for our two parent functions. One of them with a positive exponent and one of them with a negative exponent. So that's the same stuff that we had when we were just introducing our generic growth and decay functions. Just we have an e in there now, and it's got this power r that wasn't there before. In terms of the horizontal asymptotes, which yes, these functions both have, just as do the growth and decay functions we looked at in the previous two sections, the horizontal asymptote is still found when I have a vertical translation of my graph. So when I have this d value, right, plus or minus a constant, that tells me where my horizontal line is shifting. It's going up or down, whatever the value of d is then. So we make sure we want to include those horizontal asymptotes in the discussion or in the graphs of these functions. In terms of domain and range, the domain is still all reals, and the range is going to be either greater than my horizontal asymptote value, or if I've reflected vertically, I would be less than that horizontal asymptote value. So let's try a couple functions and see what we get here. So here we have, again, identifying the pieces. We've got a vertical stretch factor of 4. I see my r value is 0.5. There is no left or right. So in terms of my starting point, which again is an imaginary one, imaginary start point would be 0, 0. And remember that these imaginary start points, we don't physically go through them. And y equals 0, again, the d value is your horizontal asymptote in this problem. So we put our horizontal asymptote in there, y equals 0. Then if we're talking about our movements for our table, our parent function, we have left 1, 1 over e to the r, 0, 1, 1, e to the r. Well, our e to the r is the e to the 0.5. And each of these y values are going to get multiplied by our vertical stretch factor by 4. So I have times 4 for each of these components. So what would I have? I have 1 over e to the 0.5, that thing times 4. And let's see what we get here. So I would do my e to the 0.5. I would reciprocal that value, and then multiply it by 4, and I get 3.8. And then 4, and then e to the 0.5 again, and then that number times 4. Give me 4.21. Okay. Oops. My first number's off. Yeah, my first number should be 2.43 here. Approximately. All right, so my graph should go through those points, or those movements, and see what we end up with here. Starting point here, go left 1 up 2.43. So left 1 up 2.43. Don't go up or down, but move up, or don't go move right or left, move up 4, and then move right 1 up. 4.21, something's not right there. Let me see, let me recheck my value here. E to the 0.5. I think I was doing 0.05. Yep, 6.59. All right. So this should be 6.59. So right 1 up 6.59, and yep, there I am right there. So there are our movements, and there's our graph. Try this one. Now we introduce, we have both a translation left and right and a translation up and down. So we have our translation vector -2, -4. But vertical stretch factor is just 1. R value is now -1.5. Our C value is a 2. Our D value is a -4. So from these two, remember opposite of C and D becomes our starting point. So our imaginary start point is now -2, -4. So we're starting down here is our imaginary start point. All of my movements will come from that spot. And then we go ahead and do our critical movements. Left 1. Now for a negative E, we just said it was e to the r here, because we're going to take the opposite of that and make it become positive anyway. 0, 1, 1, and 1 over e to the r. And nothing is getting multiplied with those values. So our e to the 1.5 is equal to something. This is just going to remain a 1. And then our 1 over e to the 1.5. All right, so let's make sure I put these in correctly this time. So we're going to do our e to the 1.5 power. Is 4.48. And then we take the reciprocal of that, and we get 0.22. So those should be my movements then. my left-right movements, my up-down movements. And let's see what we get. So left 1, up 4.48, 1, 2, 3, 4.48, right about there. Left nothing, up 1, right 1, up 0.22. And there's our graph. We have a d value, so we also have a different horizontal asymptote. It's hanging out right there at y equal -4. So we got to make sure we put those in when we draw these exponential functions. All right, we've talked about, for finance, how we can compound our interest and what that meant was your interest sits in your bank and it gathers interest so many times a year. And that is based on what we call a compounding period. And this was the equation that we had for compounding periods. We had some amount is equal to a principal, which is our initial investment, and then times the quantity 1 plus what r over n, and then that to the nt power, where n was representing the number of compounding periods. And we said that if I was compounding semi-annually, that's 2. If I was compounding monthly, n would be 12. If I was compounding quarterly, n would be 4. Daily, n would be 365. Well, what if that n just keeps going and getting larger and larger and larger? Well, we see here that there is we talked about where e came from, and we can actually physically see there's that expression again, 1 plus r over n to the n. And as that n continues to get bigger and bigger and bigger and bigger, that just became e. And so now this helps us come up with what's known as our continuously compounded interest equation, called the per shampoo equation. And we get A is equal to P e to the RT power. So we will use this when I have a situation where I'm continuously compounding, and I want to make sure I'm looking for that word in the application problem. So here we're continuously compounding. We're going to invest $3,000 into an account that's paying 3.5%, and we're going to do this for 3 years. So identifying all the components, there's my principal amount. Here's my R, which I will want to make sure I convert to a decimal. So we take our percentage number divided by 100, and I get 0.035. And then here's our t value, the time period. Well, our time period is per year, but we're investing this for 3 years. So if I'm just going to go with my PERT equation here, and again, good habit, just write down the generic equation every time. The more we do this, the more we become familiar with it, and we memorize it. Let's put in what we have. So $3,000 e to the 0.035 r, and for 3 years. Now, when I put this in the calculator, I probably want to do this in chunks. I want to make sure that I do the exponential piece first, so the 0.035 times 3 becomes 0.105. So 3,000 e to the 0.105. And then I'm going to do this piece. So I'm going to do e to that number, and I get 1.11. So now I get 3,000, 1.11. And then our answer, again, approximation, is, we're going to the cents here, but $3,332.13 would be my amount after 3 years. So there's our function there. Just letting my money sit for 3 years with that interest, I'm going to have $332 more in my account. All right, so we can see this in application in the finance end of things, but we can also see it in the sciences. here we have bacterial growth. We have the growth of the bacteria, Mycobacterium tuberculosis, can be modeled by the function P of t is equal to P sub 0 e to the 0.116 t power, where P of t is the population after t hours, and P sub 0 is the population at t equals 0. Again, P sub 0 is our initial population. At time 0, we're assuming we're starting with nothing here. All right, at 1 p.m., there are 30 Mycobacterium tuberculosis bacteria in a sample. Write a function for the number of bacteria after 1 p.m. So writing a function, again, that's going to be our modeling right there. We're writing a function. Function is comparing two variables, two different quantities. We're, in this case, comparing population and time. And we were going to do this from a situation where we have 30 Mycobacterium in the sample. And we're starting this at 1 o'clock, so we're modeling since then. So in our problem, we've got an initial amount. This can be our initial amount. And therefore, our model would be our P sub 0 is replaced with 30, e to the 0.116 t power. So there's our model from 1 p.m. So for part A, we get that. Now, if we graph this, again, we've got a stretch factor vertically of 30. I've got an R value of 0.116. So if I put in my critical movements for this table, I would get a graph that's going to look something like that. And now we can use this to help ourselves answer the next question here. C. What is the population at 5 p.m.? Now, eventually, we're going to be working with how we can answer time questions from here when we talk about logarithms. I can answer this question either plugging values in for t, coming up with the equations answer, or I could look at the graph's solution. Obviously, plugging into the function is going to give us a more exact answer. If I did that, I notice that 5 p.m. is 4 hours away from when we started. So this would mean that I would have a t value of 4 that I would have to plug into that equation. Well, we could graphically go represent this. So we have a value of t equal 4, and here it is right here. T equals 4, and I go up and I meet my graph, and from that point I would project over horizontally, and then I would determine, it looks to be about 48 if we were to guess. So appears to be 448 coordinate on this graph right there, and I can go check that by plugging 4 into that function and see what we get. It looks like our population is about 48 bacteria at 5 p.m. Describing how to find the population at 3:45. Well, we could do the same thing. We could project from a 3:45 point on my x-axis up to the graph, intersect the graph, and then project to the left over to the y-axis and come up with my value. Or, at 3:45, we'd have to figure out how many time periods does that represent. Now, we're talking each t is an hour, but here we have minutes involved. Whoops. So, if we started at time 0, which is 1 p.m., now we're going to some other time value, which is 3:45. Well, it's at least 2 hours. And then how do we convert our minutes into hours? Well, we have 45 minutes, and there are 60 minutes in 1 hour. So we're just using a little dimensional analysis conversion here. And we get 0.75 hours. So this would represent a difference of 2.75 hours, which would become the t value that I would plug into my equation. So I could plug in 2.75. And then from there, I would be able to get the population growth at 345 people.